To introduce Sonia Calvari, who somehow is standing up and somehow might be smiling. She left Calabria at about 5 a.m. yesterday morning. She got on a boat, she traversed to Messina, she drove down to Catania airport, she got on a plane, the plane broke down. She spent the night in Paris. She got on a train at 7:30 this morning after 3 hours of sleep. She arrived here at 10:30 this morning. And now he's going to give you a presentation, so I think she deserves...
So if I say something wrong, you know why.
Where she just falls over. You know why. So Sonia completed her PhD with Harry Pinkerton at the University of Lancaster in the 1990s. That was very much focused. There were a number of lovely papers came out of that, including the geology of the south and north walls of the Val del Bove on Etna, a history of the southeast crater up until that date, as well as what remains my favourite paper of all time, the description of Etna's 1991 to 1993 eruption. Everyone talks about multidisciplinary today like it's something new. Sonia did it in that paper. She put everything together from textual to petrological to temperature measurements to geophysical measurements, and did the most complete description of an eruption, a very complex eruption that I still think is the gold standard. After her PhD, she went to IIG, which is now INGV, section Catania, which is now section Observatorio Etnea. She's worked on pretty much every eruption Etna's had since 1995, which if you count all the fountaining events must be 300 or 400. Several hundred, but probably her true love is actually Stromboli.
Yeah.
So she's also published on the geology of lava flows on Stromboli, the dynamics of eruption plumes on Stromboli, and the stability of the flanks there. Today she'll be presenting some work that she's putting together with Sandro Bonacorso. I believe it's in preparation for a paper to EPSL, mostly about the dynamics of lava fountaining on Etna, but there will be a little bit of Stromboli as well.
Okay. Thank you, Andy. Thanks to all of you for being here this afternoon. And thanks also to Andy and Lucia for inviting me here. I prepared this talk, to be honest, not for such a broad audience, so I hope you understand. I would have liked to show you some preliminary results that we are getting on the lava fountainings on Etna, because this is still an open topic that we need to investigate even more, so any hints, any suggestion would be very welcome. So we started with Sandro Bonacorso in comparing the data from a volcanological point of view and a geophysical point of view. And I have to confess that merging these two different disciplines opened very much my mind, especially to the speed of these processes, because I didn't think that lava could make in such a fast way from the source region to the ground. So just a view of what Etna is a big volcano, apparently the largest of Europe, is up to 3,330 meters high, 40 kilometers wide along a east-west direction, and 60 kilometers long north-south. And there are a number of people living on the flanks of the volcano. This is why we have to investigate these processes in order to predict what's going to happen next, if we can, and also to protect the people living on its slopes. Starting in 2001 and then increasing in 2002 or 2003, the activity of Etna became more explosive, or at least the lava fountaining phases, especially during the opening phases of flank eruptions, became very important. So important to impact seriously on the population, on the airport of Catania, which is a major international airport, probably the biggest of the South Italy. And we had to face with this peculiar activity for Etna, because this volcano is mainly effusive. It's very well known for its lava flows, for its lava flow fields, like Andy pointed out earlier. So we started in studying these important explosive phases, and we came up also with a definition of this activity, which is not really in everything comparable to the typical Hawaiian lava fountainings. This is because normally Hawaiian lava fountainings are occurring at the starting part of a flank eruption. They may last for long or short time, but normally they do not cause these huge eruptive columns and ash plumes like Etna does. And in comparison with the Hawaiian counterpart, Mount Etna also produces these lava fountainings normally for a short time, only half an hour, 1 hour, and especially not all of them are related to the start of flank eruptions. So this is something that we have to investigate more and understand more. But since 2000, let's say, the problem with ash plume on Etna became increasingly more important. Here is a view of the starting phase of the 2002 eruption that started on the south flank of the volcano with the opening of this eruptive fissure, and then propagated to the north along what we call the Northeast Rift, which is a place where normally flank eruptions occur. And you can see that the ash was produced essentially by this explosive activity that sometimes had also interaction with groundwater. So there was also some phreatomagmatic phase in between this eruption. Actually, inside this crater, we had something like 3-4 vents active at the same time. And sometimes we had strombolian activity in one vent, lava fountaining in another, and phreatomagmatic in the next one. All of it occurring in a very small zone, in a very small crater, only a few tenths of meters wide. So something very peculiar that was already described in the literature, for example, during the Ukinrek eruption in Alaska in 1975. You can see that the ash plume from Etna has impact also on the wall eastern flank of Sicily, sometimes also in Calabria, where there is another airport, and the ash from Etna arrived also to Greece and to Malta very often. So it's a very important impact also in the nearby population. Sometimes the ash is blowing south towards the airport, and this is another major problem that we have to face. So this is just a summary of what happened during the last few years on Etna. We had 66 lava fountain episodes in 2000 that eventually were leading to the flank eruption of 2001 and 2002. Then we had quiet lava effusions in 2004-05, 2006 twice, 2007, and another major explosive phase in 2008 that was followed by the 2008-09 flank eruption. Then we had a year of pause, and again another phase of lava fountainings. These have been very peculiar because we had between 2011 and 2014 something like 44 lava fountain episodes from the southeast crater. The southeast crater that formed in 1971, but then grew up quite a lot with this activity that was taking place from a pit on its eastern flank, and the proximal accumulation of the spatter from this lava fountainings event eventually caused the growth of a new cone. So we had 25 episodes between January 2011 and April 2012. 18 occurred in 2011 and 7 in 2012. Then in April 2012, this activity stopped, and we had the release from the volcano of quiet effusion of lava within the Bocca Nuova crater, which is one of the summit craters located here. That was essentially erupting degassed lava. There was a little bit of explosive activity, some strombolian explosions that led to the growth of a cinder cone within Bocca Nuova, but not much. Most of it was effusive, and the lava accumulating within the crater. Then again, in 2012, we had again the start of these lava fountaining events from the southeast crater. Here is a view of a few of them occurring in 2011. You can see that compared to Hawaii, we have this development. Most of the times, virtually all of them, cause this eruptive column that rises up to several kilometers above the crater, many times between 9 and 12, so they are very important, and the ash is coming out by the blowing wind and then falling on everywhere around the volcano. Then we had 7 more episodes in 2012, stopping on the 24th of April, and this is the growth of the southeast crater. I'm showing up and down to let you understand how fast was the growth of this new cone that we call New Southeast Crater in just a few months in 2011, just because of the proximal accumulation of spatter from the lava fountaining events. The survey that we eventually did on the southeast crater to measure the size and the volume allowed also to compare this data with the volume that we calculated for each single lava fountaining event, and was pretty much something like 50 millions of cubic meters. Then to study from a volcanological point of view these lava fountaining events, I used essentially the monitoring system that we have deployed on the volcano, and consists of a number of visual and thermal images deployed mostly to the south, but sometimes also on the east flank of the volcano. This is from example EMCT is from the east view, and allows to view also the spreading of lava flows within the western wall of the Valle del Bove, which is this big depression that cuts the eastern flank of the volcano. And this view allows us, with clear sky, to follow also the growth of the lava fountaining events and the formation of the lava flow field. But we have also a faraway view from here, south of Catania, something like 17 kilometers from the summit craters, which allows us to view both the sides of the lava fountainings, but also, in case of eruption, of an eruptive column, and many more images that allow us to understand how is the development of this activity. So this is the first paper that I published on this topic, and it was published in 2011. And we compared a number of different data to try to get a wide picture of these paroxysmal events. So paroxysmal for us is something a little bit different from the Hawaiian counterpart, because it develops in a very short time, half an hour, 1 hour at most, even if we had a few examples lasting longer, but normally they last something like half an hour to an hour. They develop lava fountainings that are up to 800 meters high, but sometimes also 2,500 meters high, so really impressive. And from them, many times, we have also the formation of this eruptive column, a sustained eruptive column, that normally starts after half an hour from the start of the lava fountainings, and the ash remains into the atmosphere for several hours and days sometimes, depending on the weather conditions. So in this study, we analyzed the thermal images from the fixed network of web cameras, and we counted the number of explosions. We saw that each of these paroxysmal events normally start with the appearance at the southeast crater of this strombolian activity. The number of strombolian explosions increases with time until they reach a phase that they become uncountable. And this is when we think the lava fountaining starts. I say we think because we cannot be sure. If we consider the temperature, in fact, we have a gradual growth of the temperature, which means that we pass from the strombolian phase to a transitional phase and then to the lava fountainings. So from just a volcanological point of view and from the view of the web cameras, it's not really simple to distinguish the time when the lava fountaining starts. We can do it better comparing this data with the strain meters, which are these instruments located in deep holes in the ground that do not get affected very much from the weather conditions because they are located in a deep hole. They are very sensitive to the ground deformations, and they can they show, I will show you later, a very sharp jump in the signal as soon as the lava fountaining starts, because this corresponds to the sudden emptying of the source region. So analyzing this data, we could measure the height of the lava fountainings, and we could calculate the volume of the pyroclastics erupted during the lava fountainings. We could also use both helicopter surveys with a thermal camera to map the lava flows, and also use the satellite images like we did many times with Andy and his students to obtain also the volume of the lava flow erupted normally together with the lava fountainings. Here you can see, I hope you can see, the spreading of the ash on the south flank of the volcano from the lava fountainings of January 2011, and the lava flow spreading on the Valle del Bove. Normally, the lava flow do not reach more than 4 kilometers, so they do not pose any danger for the population because the Valle del Bove is a desert place. But as I said before, the ash has strong impact on the population. Together with this data, we were also using a comparison with the SO2 flux that we measure from a number of stations deployed on the flanks of the volcano. First on the east flank, because this is where the winds are normally blowing, but now we have a complete circle of instruments that can measure from the morning to the evening, because the SO2 flux uses the sky as background, so it cannot be measured during night. This is why we have very often partial data. But anyhow, we could detect a sudden decrease of the SO2 flux just before the start of lava fountainings, which we explained with the accumulation of this foam layer on top of the magma chamber, which is normally recognized as the French model. So it works, at least on Etna. We have this accumulation of gas, SO2, but not just SO2, mainly water and CO2, that is suddenly released as soon as the lava fountain starts. Then we started in measuring these events. We had, I said before, 44 episodes, paroxysmal episodes, between 2011 and 2013. And we started in measuring the lava, as I said, through surveys with helicopter or satellite images. We measured the pyroclastics, the duration, the total volume, and the mean output rate. And the 44 episodes that the Southeast crater produced between 2011 and 2013 had almost the same value. They release almost always 2.5 million cubic meters of lava, which we think is the size of the shallow magma chamber located below Southeast crater. This shallow magma chamber has been located at about 0 meter above sea level, so at the sea level, and it has been located both using the volcanic tremor and also the strain meters, inverting the data from the ground deformation system and also localizing the amplitude of the seismic tremor we could detect the position of this magma chamber that has been always in the same position for the 44 events that we had between 2011 and 2013. Then we analyzed also the strongest of these paroxysmal events. These occurred on the 23rd of November 2013, and this is the first event of January 2011. You can see the difference of the size of the lava fountaining portion, the white portion. Here is 800 meters. Here I think reached 2.5 kilometers above the crater. This was a sort of other end member of the system because there was no lava flow erupted. It was very short duration, only 45 minutes, and the pyroclastics were up to 1.5 millions of cubic meters with a very high mean output rate, 360 cubic meters per second, and the source region was always the same. So we were intrigued in trying to understand why all these episodes from the southeast crater have been comparable between them, always the same volume, and this one was instead without lava flow, very explosive, and with such a huge lava fountaining and eruptive column that you can see here. Here you can see at the bottom right the strainmeter signal. You can see that there is a sudden decrease of the signal as soon as the lava fountaining starts from the summit craters. So we were analyzing all the data for all the lava fountainings, and we published a lot on this topic, tried to obtain the lava flows from satellite even when we had ash cover, and that was a big suggestion from Andy that allowed us to use the cooling rate of the lava flow to obtain the whole picture even when the data were missing. So somehow we came out with these general features of the paroxysmal episodes from the southeast crater. All of them, or most of them, start with initial strombolian activity that in a few days, sometimes also in a week time, leads to increasing intensity and then to the lava fountainings. The lava fountainings have a duration between 30 minutes and 1 hour. The average height of the lava fountainings is 800 meters, but I showed you before that we had also the other end member reaching up to 2.5 kilometers on average, because at that time the highest altitude that we could measure for the lava fountainings was 4 kilometers above the crater, just for a short time. And then the total volume, which is 2.5 millions of cubic meters dense rock equivalent. And the lava flow that normally accompanies this activity from the base of the fissure. Then we use this data, extending the paper that we did with Andy about the calculation of the output of lava from Mount Etna during the last 30 years obtained from satellite, and we updated this graph with the data from the last eruptions, both effusive and explosive. Given that Mount Etna is recognized as a steady volcano, erupting a steady amount of lava over a long time, over a long period, which is 0.8 cubic meters per second, which means something like 25 millions of cubic meters every year, we think that we can somehow predict what's going to happen next if we can take a continuous update of the amount of lava released by the volcano, both in terms of lava flow and pyroclastics. And in fact, this works, and is working even now, which means that if we have no activity at Etna for 1 year, 2 years, we know that the supply system is accumulating lava, 25 millions of cubic meters every year. So if we have for 2 years no eruption, we have accumulation at the source region of 50 millions of cubic meters, which means that we can expect that this volume is released by the volcano sometime soon, probably. This can be released in two different ways, and we cannot predict this, obviously. The volcano can decide to produce several lava fountainings, and in this case we need a high number of lava fountainings to release the volume, because as I said before, each lava fountain is releasing just 2.5 millions of cubic meters. Or the volcano can produce lava flows, flank lava flows or summit eruptions, and in this case it's faster the decompression of the system and the release of the accumulated volume, because normally we have lava flow fields that normally range between 10, 20, 30 millions of cubic meters. So the volcano, depending on some parameter that we don't know yet, can decide to produce either lava fountainings or lava flows. This is something different compared to what was happening before, because normally, before 2000, we had the lava fountaining phase strictly associated to flank eruptions. So we had the fire fountainings at the start, releasing the gas-rich magma, and then the gas-poor magma coming up later with flank effusions. This time, no. For some reason, something has been changing in the supply system, not as a total amount of magma stored in the system, but as a way of releasing this volume. So our studies are focusing on understanding why and how. After this phase of 2011-2013, in fact, probably the magma accumulating inside the magma chamber was poor of gas. In fact, we had again a number of quiet lava effusions from the flank of the southeast crater. And here is a view of the main parameters suggesting when lava fountain is starting. We have a first, this is a very recent image of 28th of February this year. We had more modest lava fountainings from the southeast crater this year. And this activity started with ash emissions that passes to strombolian activity and then to lava fountain. And together with this progression in the activity, we saw also a progression in the location of the volcanic tremor. The volcanic tremor, which is normally located at this depth, is moving upwards up to the crater band as soon as the lava fountaining approaches. And here is a view of the amplitude of the volcanic tremor. You can see that there is a sudden jump when the lava fountain starts, and we use this jump to advise the civil protection on time, because the first and second alarm released to the civil protection are related to the speed up of the process just in this phase. Here is a view of a thermal image showing a very recent lava fountaining event of February this year. Also, the infrasound changes. The number of infrasound signals increases dramatically when we approach to a lava fountaining event, and the signals locate to the vent that will be producing this lava fountaining, the southeast crater in this case. And here is a view of a graph automatically released by the thermal camera located at Nicolosi, which is something like 15 kilometers from the vent. That is showing how the temperature, even recorded from such a long distance, increases as soon as we have the passage from strombolian activity to lava fountainings. So back to the topic of today. Between the 3rd and the 5th of December 2015, we had 4 paroxysmal episodes from Voragine, which is the oldest crater, the oldest of the summit craters of Etna, and which is normally silent. I think it did not produce fire fountainings for over 30 years, but then suddenly entered into action in December 2015, causing 4 events in a very short time, in just 3-4 days. For the analysis of these events, we used thermal images recorded by these web cameras, and also 3 strainmeters that we have located on the west flank of the volcano at different distances, because with this we can delimit the position and the depth of the source region. So here is a view of the first episode, occurred on the 3rd of December 2015. Here is a view from Nicolosi, which means from 15 kilometers south of the volcano, and you can see the huge lava fountaining formed. Here is a view from Montagnola, which is very close, only 3 kilometers from the summit. And here is a view from a visual camera at La Montagnola. And here is a graph of the elevation of the lava fountainings. You can see that sometimes we reached also 4 kilometers above the crater. And something like 200 meters are obscured by the rim of the crater, because the vent is located inside the crater at something like 200 meters depth. And here is a comparison between the elevation measured by Nicolosi, which is this camera here, and that of La Montagnola, which gave a partial view, because you can see here that the maximum elevation of the lava fountaining is cut by the field of view of the camera. By comparison, here is the second episode that was already entirely detected by La Montagnola. And here is a view of the eruptive column forming on top of the volcano. The eruption occurred during daytime, so this time it was very well visible. And here is a measure of the elevation of the lava fountainings with time. This is very important for us because it allows us to calculate somehow the amount of pyroclastics released during each episode. This is the event occurred on the 4th of December p.m. You can see that it's much smaller, and this is eventually the 4th. The 4th, we had unfortunately poor weather conditions, so it was not detected at all from Nicolosi, but we could see it entirely from La Montagnola crater. You can see that the elevation of the lava fountainings was very minor compared to the others, but the duration was much longer. We could obtain somehow the total erupted volume from a survey that we did with thermal camera and visual camera by helicopter just a few days after this event. And we obtained a new DEM of the summit zone, and we could calculate a sort of erupted volume, which is unfortunately only the proximal erupted volume, and it's about 7.8 millions of cubic meters. The mapped area here is 4 square kilometers, but we could also see the vent diameter, which is this spot here, if you can see it, which is very small compared to the size of the lava fountainings that we observed. And the thickness of the deposit in some places is over 70 meters. So it was a very important eruption that filled completely the craters. Here, before this eruption, we had Voragine here and Bocca Nuova, the 2 vents of Bocca Nuova in these 2 positions. So the crater was completely full with lava. Sort of lava because the spatter being confined within a crater were immediately welded, very much welded. So this time we used the strainmeter signals to try to compare this data with that obtained from the thermal cameras. Now, from the thermal cameras, in reality we do not obtain the volume of pyro in the lava fountainings. We obtain the total mixture of gas and pyroclastics. So in order to obtain the volume of pyroclastics, we need to make some assumptions on the ratio. We used the ratio of 0.35, which was suggested by Parfit, analyzing the Hawaiian lava fountaining. So we suspected that on Etna, this ratio could be different. In reality, we understood that it's different not between Hawaii and Etna, but it's different also between one and another lava fountaining on Etna itself. So the situation is very complicated. And also trying to obtain this data, comparing the data from the web cameras with the data from the strain meters, which measure the mass released by the source region, is quite complex because the mass contains gas and we don't know the proportion, the exact proportion. But somehow we could first of all see that the sequence of the episodes from the voragine were fed by a source region that was deeper than the one that was feeding the southeast crater. The previous was at about sea level. The one from Casmi is located 1.5 kilometers below sea level, so it's deeper. In addition, the lava fountainings from Casmi did not produce any lava flow. It was just pyroclastic material. So somehow the depth of the source region allowed more gas to be mixed with the magma and then a greater explosivity of the events. That was decreasing with time, because you can see here from the strain meter signals that we have smaller and smaller and smaller signals, which is compared to me with this episode of the 15th of March 2007 occurred at Stromboli. Consider the different sides of the two systems. Stromboli is a small volcano with a small supply system and small volumes being involved in the eruption. I would say several orders of magnitude smaller. But still, the 15th of March episode, this is again a strain meter signal, so three different inputs of decreasing intensity in just 2 minutes perhaps. The same apparently occurred on voragine, on Etna. It took longer time because the size of the source region is bigger, but this is what happened again. And we think that having this decreasing, having observed this decreasing volume with time, can allow us, if another eruption like this happens in the future, to predict somehow that the sequence of explosive activity is finishing. Because this is what happened with voragine. Produced these 4 episodes of decreasing intensity, smaller volumes with time, and eventually the explosive activity finished, and the activity at the volcano continued with just small lava flows coming out from the southeast crater, degassed lava released by the system. So we would like to improve these studies to understand more, and if possible to obtain the real amount of pyroclastics released with time in a more constrained way, let's say. We tried to do it for the southeast crater, comparing the size of the cone with the total amount of pyroclastics that we computed for each lava fountaining event. And we saw that for southeast crater is stable, like if the shallow source region was in a sort of stable condition. Here it's not stable for some reason. And we would like to improve these studies to understand more and more, and if possible to predict more. So this is just a final comparison between the episode from voragine and those from southeast crater. So a more gas poor magma, no, a real gas poor, because you saw that it can cause also fire fountainings like 4 kilometers, but normally poorer than the magma that is released by voragine, which did not produce any lava flow during these episodes, whereas the New Southeast crater has every lava fountaining event normally accompanied by a lava flow. The volume released by the New Southeast crater is steady, while here is decreasing with time. So any suggestion you can have on this direction is very useful to us, because this is another tricky question. Studying the lava fountainings from Southeast crater and voragine, I thought that the main difference was the amount of gas contained within the magma. Then we had a seminar from Terry Parker, which is a petrologist that you may know. She has been collecting samples in a number of different volcanoes from different composition, different tectonic environment, and she has found that the maximum amount of water contained within the magma of any composition is normally 4% of water, and this water that is normally released during the lava fountaining episodes, more than SO2, more than CO2. So if the initial amount of water is always the same, how we can get this different behavior? And especially, how can we measure water during one of these paroxysms to be able to detect the difference between one and the other? So this is the question open for you. Thank you for your attention.
Sonia, hopefully you were waiting up to take some questions.
Yeah, I hope.
Hey, Sonia, are you, to what extent are you confident with your estimates of the pyroclast compared to the lava flows, for example? You have a number of assumptions, I guess, underlying your results on pyroclast estimations, right? Can you explain a little bit?
Yes, we tried. We have been at first analyzing all the images from each of the 44 lava fountaining episodes that the New Southeast crater produced. And we came up with a number. Then we compared this number with the total amount of proximal pyroclast, let's say, that gave rise to the cone, to the New Southeast crater. So we knew that the volume, the erupted volume, had to be of the same order of magnitude, like this. And we came up with this ratio, which is normally for the Southeast crater, 0.18. But then we came up with the event of the 23rd of November, which is really different from the others. So there we assumed a ratio, but we cannot be sure that this is true. Also, the strainmeter signals, they somehow are related to the amount of mass released by the source region. But there is also some compressibility of the magma due to the amount of gas dissolved within the magma, which can be variable from one eruption to another. So it's very difficult to constrain unless we have independent measurements of water released during a lava fountaining that we can compare in order to predict. Because if we measure the crystals, like Terry Parker told us, we will get always the same amount of water, 4%, which is the original one. So I suspect that somewhere into the feeding system we have the accumulation of gas mixed with magma that drives the activity in different ways. But how this happens and when and why is still a matter of study. So any suggestion is welcome.
For this number, I might have a suggestion for a way to compare the mass eruption rate or the total mass from an eruption to another, paroxysmal deposit to another, could be to exploit the radar data, in particular the one we have, because we have developed in recent years a method to get a mass proxy out of this data, and we have some difficulty to calibrate in absolute fashion the mass eruption rate or the total mass if you integrate over time, but we are quite confident that they are comparable to one another. So it could be a good way. I don't know if the information could be useful, but I understood that it was one information that you were missing. Yeah. So I think that's something that could be implemented quite easily.
I forgot to say one thing. We are proposing a frontiers topic for the journal Frontiers in Volcanology, which is about this activity, and not just on Etna, everywhere. So you're very welcome to submit your papers, and especially if we can join different kind of data, that would be really fantastic. Because comparing the Voldrad with the volumes that we obtain from the thermal camera would be a way to get the water in a different way, you know, subtracting the pyroclastics instead of subtracting the water like we do normally. And comparing also with the strain meters will be really fantastic, because we can try to define some system that may work also when we have no data, no Voldrad data or no camera data, because there is no visibility. So it would be nice to obtain a law that is applicable to different.
To get the volume of PR class, you're always using the height of the lava content from the videos, the thermal videos, then you multiply that by some coefficient that is quite uncertain at the moment, and then by the vent area that you measure after the event.
And we have the vent area only for the southeast crater, because we published in the 2011 and there was no significant change in the size of the vent.
So you're monitoring that from another an event to another?
We use always the same size, yes. And Voragine, because we mapped the summit and we saw the vent.
Are you confident with the accuracy of the vent through time? Because it's a matter
through time, you mean for the southeast crater?
Yeah, but you always using the vent area. You say
it did not change.
It didn't change. So
no, we did many surveys later on, and it did not change.
Some of the activities seem to have many different small vents.
Yeah, but the vent producing the lava fountaining, the 44 episodes, I mean, the one that is producing now, no, is a different one. But the 44 episodes was always the same vent. So if you need 1 meter more, 2 meters more, but the size is.
I think there's some questions over on the left-hand side.
Okay.
Okay. It's, so the water content that is measured is reflecting the water content in the magma chamber.
No, we don't measure the water content, unfortunately. This is the problem.
You said that someone measured the water content in your samples.
No.
Ah, okay. So you don't have melt inclusion. Ah, you don't have
the melt inclusions.
You have no idea about the water content in the magma chamber.
The melt inclusions give the original content of
in
water.
the magma chamber.
In the magma chamber at very depth, not
so
the one located at 1.
And you have those. You have those.
It's always 4%.
So this is what I understood.
This is the problem.
So I understood correctly.
There is no difference.
At Etna, it's always 4%. Or are you talking about this global?
This is what
global.
Ah, but we mean at Etna. Is it always 4%
yes,
at Etna?
the next step is, in fact, Terry Parkes is trying to work on Etna samples now to see if there is any difference. But she's confident that she will not find any important difference, because andesitic, basaltic, dacitic magmas, all of them gave her.
Yeah, but
this is what she said.
That's not true. You go to Vesuvius, and 1944, 1906, you can see different water contents. In Stromboli, you have different water contents.
Can I comment on this? So basically, what Terry is doing is she's looking at this evolution trend on the cilium water ratio and try to
We know
extrapolate to
this
the
paper,
source.
yeah.
But-
Terry Plank,
but,
yeah.
Can I finish?
Okay.
But what happened is that she gets around 4%, but she never said 4.0%.
Yeah, she
Her
does.
data itself has a spread.
Yes, it has a spread, but 4% is
So it's just a hypothesis, it's around there, but we cannot say it is 4 sharp. It could
That's
be
what she
5,
said.
it could be 3, you know, so that.
You're right. In fact, she's trying now to investigate the lava fountains from Etna to see if there is any systematic difference between different episodes. But the fact that she found 4% in basaltic and andesitic magmas, I think is striking. And she explained this as the amount of water can be contained into the mantle. She said that cannot be more than this.
It's the
This is her hypothesis.
hypothesis.
I'm not a
is the,
petrologist, sorry.
The counterbalance between the amount of the water melting can produce from the amount of water added. So more water you add, you melt more, so therefore you balance.
Okay.
The end. That's the idea.
So, so because I understood that you were talking about your samples.
No.
So, why? Can you have your? Is it possible to measure your samples? So there are no melting inclusions in your samples?
I'm not a petrologist.
No, but can someone do it in Italy or
Yes,
in the?
but no, it
ENVG
hasn't
or
been done yet
ENVG?
on these samples from these lava fountainings. It has been done, I think, on the samples of 2000, which had volumes an order of magnitude smaller than these. Okay, so can be something completely
Nicole-
different.
Metric did it, yeah. But
So
the,
they
the
have a
amount
same-
is
yeah.
super low, it's 3%.
Nicometric.
So do they have the same water percent? This is what would be interesting.
No, I don't think you find always the same.
So there is a variation in the water
but not big,
contained in the magma chamber.
Like at Piton, the water percent is always around 1, no more than that.
But what I think is that the amount of water that you get from the melting inclusions is not the amount of
they're
water
looking
mixed
at, yeah.
with magma within the shallow chamber. Because olivine, I'm not a petrologist, but I don't think that olivine forms at
No, you're right, it's
1
deep.
kilometer below sea
That is the
level.
main
It forms much deeper. So the original content of water into the magma can be very different. But then something happens into the migration towards the surface that changes this equilibrium.
You check, for example, the olivine of Stromboli, and the last, the one that formed last in the shallow system, at 500 meters, don't have any. The system is completely degassed.
So there is the gassing along the path that changes the
And so you
properties
change,
of
and
magma
you
and
don't, it's difficult
the
to quantify this.
explosivity of magma.
So it means there are fissures, je sais pas comment dire. Cracks and, I mean, it means that from one regime to another, the edifice, the volcano, is either closed and functions in a closed system or an open system.
You can see very well from the ground deformation data that I showed you here. This is sudden deflection of the source region related to the release of magma during one lava fountaining. This is just a few minutes, I would say, half an hour. During half an hour you have the sudden deflection of the edifice, and then it inflates again and then deflates suddenly again and again. And this happens every time we have a lava fountaining. With a source region located 1.5 kilometers below sea level. So this is, I think, really impressive because it tells you the speed of the magma rising from this depth to the surface.
Thank you.
It's okay.
It says expansion. Is deflection?
Deflection. Yes.
It's expansion on
Yes.
reversal.
Sudden deflection followed by inflation. And sudden deflection.
Because it's increasing contraction, expansion. It's the wrong way, right?
This is related to the system, to the instrument. The
So we have to
instrument
understand
has
deflation is-
Yeah, but this is the deflation of the source region, the decompression, right? which causes expansion means that the bubble of the instrument goes up, but it's related to a contraction of the source region. So it's something like mixed up, but the meaning is always the same.
Sonia, you show well the passage between strombolian and then lava fountain. What about lava fountain into ash?
What do you mean?
I mean, what about lava fountain to the ash plume? That when you pass from, you spoke about this transition.
The initial graph.
Yeah, you showed the graph which you said this is the strombolian. Then
This
we have
one here.
then we have
Strombolian
fountain.
phase.
Yeah, then we have fountain. The real ash development plume.
Normally it happens half an hour after the start of the lava fountain, but I did not study the ash plume. We have
You didn't look at that.
no.
Okay.
We have ash starting before the strombolian phase. Normally, before the strombolian phase, we have little ash released by the summit vent, the one that eventually will get into eruption. But this is very small amount and is normally brown, like the opening of the vent.
Yeah.
Then we have a lot of ash released with the ash plume when there is this eruptive column that you can see is rising 9 kilometers above the vent. Normally it takes half an hour before it develops. But it's not always like that, obviously. And there are people measuring the amount of ash released into the plume, but it's very negligible compared
Yeah, in terms
to
of volume, it's nothing.
Yeah,
Yeah, because I was wondering, I mean, Daniele does a lot of isopacks, but you are looking only at the proximal coarse deposit
Yes.
formed by the fountaining.
This is also for a different reason, because they want to advise, the airplanes
Yeah, of course.
for different the fallout on the floor, on the surface, because of the stability of buildings, roofs, and things like that. But for getting the total volume, the problem is that we have the proximal volume, which is the growth of the cone. We don't have the one in between, because Daniele and also Simona, when they are measuring the ash released by the plume, which is 10 to 5, very small
This is-
amount
of
compared,
course.
but it's from 4 kilometers far away from the volcano. So we always miss the most proximal portion, which is, let's say, from 500 meters to 4 kilometers. And obviously it's impossible to get samples there. We can sort of extrapolate the graphs to get an idea. We use 30%, but can be 20, 10, who knows?
Yeah, no, it's, yeah.
It depends on the wind, on the size of the class, it depends on so many things. Okay?
You mentioned that prior to the fire fountaining, you see a decrease in the SO2 flux, and you attributed that to the accumulation of gas-rich foam.
Yes, this graph here.
What do you think is actually causing the change in the system from the accumulation of the foam from just normal degassing?
I think it's the size of there is no real change. It's the size of the system that does not allow too much gas to be released suddenly. That's why it accumulates. There is a model published several years ago, I think in 1998, by Vergnole-Jopard, which shows a sort of roof of a magma chamber where the foam accumulates and until it reaches a sort of threshold value and then eventually breaks into the conduit, forming the lava fountain. So I think it works pretty well for Etna, and is somehow is proved by this graph, even if this is just SO2, but we know that SO2 flux somehow behaves like water during the lava fountain events.
How long before the events do you see these decrease?
Don't remember, because this is not the study one.
Or
The
rapid?
study one is here, and the lava fountain occurred at night, so we don't know precise. But I think 1 hour, not much. I think it's an hour before the start of the lava fountain. It's very rapid. This is surprising, actually. Very rapid. I was expecting, to have accumulation for days, months, and instead it takes nothing to move the magma from depth to the surface. And we know this thanks to the strainmeters and the ground deformation signals. Another interesting thing, we would like to obtain the speed of rise of magma, because probably this makes the difference. But we don't know yet. We have to study more.
Great. Thanks very much.